Yeah, well, my talk will be rather short actually, because talking about analytical aspects, there are not that many new techniques in analytical chemistry. So what I will talk about is rather problems that you may encounter with very standard techniques, and then I will focus about importance of mineralogy and some microscopy procedures that may help you to understand the samples a bit more. So my talk is split into two sections. First I will talk about graphite analysis and then switch to lithium. And so I will start with graphite properties. So graphite is an allotrope of crystalline carbon. On atomic level, it consists of flat sheets that are thank you, that are not really bonded chemically to each other, just electrostatic attraction. It has hexagonal crystal structure. Graphite decomposes at 600 degrees in oxidizing conditions. The melting temperature is quite high, is above 3000 degrees. In non-oxidizing conditions, graphite is a thermal and electrical conductor, and it's chemically inert. And there are two major, basically, methods to estimate graphitic carbon content. The main one is using a carbon sulfur analyzer. The sample preparation usually consists of pretreatment of the sample with acid to remove any carbonate content, and either ashing or using hydrogen peroxide to remove organic material. Later on, the sample is basically followed by analysis with the infrared carbon sulfur analyzer. Now, each lab would have different methods and to pre-treat the sample and analyze it. Geological Survey of Canada had looked at 7 different methods of analysis and found that all of them gave slightly different results, up to 5% of total graphitic carbon. And one of the reasons is usually, depending on mineralogy of the sample, you may need to have a slightly different procedure for acidic, pre-acidic treatment, as well as removal of organic content. So if your sample has more say carbonate material than a usual sample that was used to for method validation, you may need to have basically spend more time to remove the carbonate content. The same applies to organic material. The time that is allocated for pre-ashing, for example, of organic may not be enough actually to remove all these impurities, and that will affect the final basically analysis with carbon sulfur analyzer. Using appropriate reference materials is very important. They should ideally match your sample as well. So if you have a complex mineralogy in your sample, try to choose reference materials that match the matrix the best. Another method is loss on ignition. It's relatively simple, used very frequently for a big set of samples. It's a useful screening tool where the sample is, the graphitic content is measured as a weight difference after loss on ignition at 1000 degrees. And here as well, mineralogy can make a difference. If your sample has, again, some carbonate material, some clays or iron oxyhydroxides, that would affect the result, as well as sulphides, because they also lose the weight basically on loss on ignition. Moreover, some minerals can actually gain loss. You have to make sure that you know your sample very well. Then another analysis you can do is to analyze impurities after loss on ignition, analysis of ash for different trace elements or major elements with XRF and trace elements with ICP or any other technique. Bulk mineralogy, again, you can perform with X-ray diffraction. X-ray diffraction looks at crystalline carbon. So you can actually see a graphite peak in a normal graphite sample, but most of the time it's used to analyze impurities, which you can relatively clearly see if they are above 1 and 3%. So for those who get confused sometimes with what X-ray diffraction can actually give, X-ray in contrast to chemical analysis, X-ray diffraction basically gives you the compound analysis. So you may have results for sulfur or iron, but XID can actually tell you which minerals that are they're allocated in, and that can help you to make certain decisions. Microscopy, as it was said before, is a very useful tool to understand a little bit more about your sample. Most common one and cheap one, I guess, is optical microscope. You can analyze size and shape of graphite flakes, do mineral liberation and association. Another more advanced technique is SEM-based mineralogy, automatic mineralogy. One of the instruments is QEM-scan. Basically, it can give you similar information to optical microscope, but under a rather higher resolution, and you can get a bit more statistical analysis. Basically, just to analyze a bit more particles, and you can get maybe information on a finer material that you can't see with the optical microscope. Scanning electron microscope on the right can give you an indication of how actually flakes look like, and you can estimate some micromorphology from that. And on this slide, I actually chose to show how all these different graphite material look like under microscope. So so-called amorphous material or microcrystalline under microscope is very fine and basically has an irregular shape. Crystalline flakes do look like flakes above 100 microns, and crystalline vein material is also has its own structure, a bit more elongated type of flakes. With the microcrystalline, I think the problem is when the size of the material is so small, it has really high surface area. So what tends to do with impurities kind of coats them, and during separation process, really hard to basically get rid of it. So that's one of the problems with, I guess, amorphous graphite. But these are the techniques you can use to understand the material a bit more. Now I'll go with, I'll talk about lithium. As we know, again, lithium belongs to alkali group metals. It has the smallest density. Out of all metals, it can flow in water. The melting temperature is 180 degrees. It's highly reactive. The flame test gives crimson red, and that's how actually lithium was found. The Brazilian naturalist, when he was in Sweden, threw a petalite mineral into the fire, and it started basically glowing red. And this feature was used in flame photometry to analyze for different alkaline metals. Okay, so crystal abundance is 30-65 ppm, so it's relatively abundant. Lithium-bearing minerals, we all have seen them, so there's nothing special in this talk. Wet chemistry, again, a very standard technique. Each laboratory has it, and there are two major methods to analyze for lithium, which is fusion with alkaline fluxes, and acid digests. And with regards to lithium, there is not much difference in the results. However, if your sample would have some refractory minerals, tantalum or niobium, minerals that contain these elements, you may not completely dissolve them in for acid, and fusion will be the most appropriate technique in this sense. Yeah, you can do lithium analysis on pretty much all geological material. It could be soil, rocks, and vegetation. Yeah, so it's very standard procedures. X-ray diffraction again. If you want to understand the mineralogy and where the lithium element is actually locked in, most of minerals that are associated with lithium can be clearly identified in X-ray diffraction analysis. There are some like clays or like micaceous lithium-bearing minerals that would not be fully resolved in X-ray diffraction, and that's on the right. Basically, what I'm trying to show, that the zinvaldite, for example, overlaps with the standard muscovite peak. So laboratory would generally report it as a part of elite muscovite group, and to understand which basically mineral you need to do a more detailed microscopic analysis. Here again I list the same techniques that can be used. Automated micromineralogy. Again, lithium cannot be seen directly by this technique because they're all X-ray based. However, the actual content estimated by difference, and usually electron microprobe is used for a very detailed chemical analysis of special grains. The lithium content estimated by difference. Again, micromorphology. Some new techniques like laser-induced breakdown spectroscopy is used directly to actually measure lithium distribution in the sample, but that's rather for, I guess, special analysis. It does require special preparation for lithium-bearing material and analytical procedure. Yes, and yeah, that's all. That's the major points. Yeah, if you have any questions, can answer them, but yeah, it's just really standard procedures. All of these processes, I think, pretty much all major laboratories offer these sort of services, although some of them look very difficult. So you can basically ask for any details, any provider that you're using. Yeah, thank you.